We're going to go a little out of order. Is Chris Mueller, is Chris in the room right now? Okay. And then after that, we'll be doing Jake Vanderplas. So is Jake here? Jake. Okay, well, if he doesn't show up, then it's Nick Labello is after that. Is Nick here? Okay. All right. Oh, and you have exactly 5 minutes. We will be signaling you at 30 seconds, and oh yeah, and there's a timer there, and we'll be caning you off the stage at 5. So.
All right. And of course, I'll spend a minute here getting this. I'm going to look at the screen and do it this way since it's not mirroring, right? So can you hear me okay? I'm Chris Mueller, and I'm from Lab 7, and I'm going to do Lab 7, we do gene sequencing software, but what I'm going to demo today is actually our Pipeline Manager product that we just released last week. And it's kind of more of a general pipeline management product, and I just wanted to kind of share it with this community. A lot of feedback from a lot of different people I've met over time in these organizations or in these meetings, led to a lot of what we're doing here. So this is our general purpose Pipeline Manager product. Basically, if you do computational pipelines, you're probably used to doing, having a bunch of shell scripts that you call a pipeline that are a task, have a bunch of tasks that you do in order that might need to execute on a cluster or somewhere else. This is a pipeline manager for keeping track of all those, for managing execution, managing data flow, and everything else through them. So this is a really simple bioinformatics pipeline up here that you can see. This is, if you do bioinformatics, you might recognize this as the standard bow tie example. But this is kind of showing what our view of a pipeline is. It's a bunch of tasks that happen in order. Some of them may get to execute in parallel. If you want to go and actually see what they're doing, you can dig right into the code view here. This will show all of the shell scripts that correspond to each pipeline. We have it's kind of hard to see on the screen right here, but you can actually parameterize these. So when you go to execute it, you can actually have the user type in a few different parameters, so file names, things like that, that might work. So let me fire off a really simple pipeline here. This one called sleep 4 times, which does exactly that. It's going to sleep 4 times. So we just got the sleep command. So I go run it, and this is telling how long to sleep. So we'll have it sleep for 4 seconds each time. It's going to run it over here. We can jump over to the monitor view here now, and we can see that it's running over here. You can actually see where in the pipeline it is down here. This will kind of advance as you go forward. So this is kind of the basics of kind of building and editing a pipeline and then monitoring it as you go on. There's also kind of an operational view of it. So if you're running a lot of pipelines on your cluster, you can kind of see all the pipelines that are in flight, see the ones that have failed. If something failed, you can actually dig into the standard error right here. We'll capture that for you. You can go in and pull that information off, restart the pipeline if you need to. And then another thing that we've added in here, so it's more than just a little pipeline engine, is we've added a report component to this too. So you have reports can be associated with the pipelines. And a really simple example right here, this is this pipeline just generates some bogus data. But the report builder right here, so this is the report builder component. So you have a bunch of different plotting elements that you can drop in here, and also just you can put ASCII text or anything else in here. So every time you run this pipeline, this report will be available, and you tell it what data from your pipeline to use when it renders the report. So I've already conveniently ran one of these. So if we go over here, we can get into, where's that one? The generate CSV file, and view a report over here. So this is just kind of showing some data from the report. We use D3 to do a lot of the graphics in here, and you can put whatever you want in here and kind of build some fairly complex reports. And then every time you run a report, it's going to have that data associated with that particular pipeline in that report or that pipeline instance. So this is kind of the basics. A few kind of just general high-level details on it. So we just released the public beta of this last week, so it's available on our website. We actually do pre-builds for OS 10, Red Hat, and Ubuntu, so you can just download it, install it, and run it. It generally works on all those platforms without any additional effort. Showing it here because a lot of it is written in Python. The whole back end is Python. I'm talking to Postgres on there, and we do HTML5 and JavaScript for all the front end on it. We have two different versions, 2 levels of support. We're always going to maintain a free version of this. It'll always work on a laptop, single user, single node. And then we have support for a lot of job schedulers and different backends and multiple users and a whole lot of other features that we'll be adding over the next couple months that really start make it more of a gene sequencing software platform. But right now, it's truly a general pipeline manager. And the one last thing I want to kind of show out here is at trade shows, we demo this on our Raspberry Pi cluster, which we always get people telling us that you can't do bioinformatics on Raspberry Pi. We know that. But it's still a lot of fun for demoing on. So we also have a bunch of information on that cluster we built on our website. So thank you.
Thank you, Chris. Next up, we have Jake Vanderplas. And then after that is Nick Lobello. So.
There you go. So I'm Jake Vanderplas. I work at University of Washington. I'm an astronomer by training, but I'm in the computer science department right now. And we've had an interesting collaboration the last year or two at UW, working between computer science and astronomy on this project, among others. And I'm going to talk about the Astronomy Collaborative Toolkit. Now, a lot of this is not Python. Some of it's written in Node.js, but I'm going to get to the Python part as well. Essentially, what it is it's just it's an interactive data visualization tool. It's a dashboard-based thing, so it runs in your web browser. I'm running it on my local host right now. You can create a dashboard and choose several different widgets that you might not want to add in. I'm going to choose 4 of these right here. Start the dashboard, and you get an interface into freely available astronomy data sets. We have a Google Sky instance here that we can use if we want to fly to any interesting objects. I'm flying to Vega, the Andromeda galaxy, the one that's near us. Oh no, sorry, that's the star. Let's go to Andromeda. That's what I meant to do. Yeah, so if we go to the Andromeda galaxy, nearest galaxy to us, we can see the images there. Astronomers in the audience, you might be interested, we can go to clusters like M67. And then this is the very cool part right here. We have a view bound here. And what we can do is generate a data set that actually generate a query that will query the Sloan Digital Sky Survey server and actually get the information for every star in this window. So if we submit that query, it'll take a second, and if the network's working, it'll load them. So we have all the objects in there that are in the Sloan data set. And then we scroll down here, and oh, did I not? Oh, shoot. I forgot to load the Sky Viewer name resolver. I need the scatter plot as well. So let's do this just one more time. Sorry about that. We'll go to M67. We'll get our data, submit it, get the stars, submit, pull those out. And then down here what we have is a way to visualize the points. So we can look at the G minus R color versus the R minus I color and get a plot there. Now this is interesting, and when I first saw this I thought this is kind of a cool toy. It allows you to look at data, and you can share the URL of this notebook. It's persistent, and it can go to, you can send it to a collaborator, and they'd be able to look at the data, and you can actually interact at the same time, working on things at the same time. But as a Python programmer, I really want a way to get at this data and play with it once we've done this visualization. So I wrote a little plugin to IPython notebook that allows you to embed this. So we'll just start on the PyLab mode, and we'll enter the URL of our dashboard and embed it in IPython. And there you can see we actually have all the data that we were looking at before with the colors, with the labels. And if we want to get at this data within IPython, we can just click this send data, and then we have it in our notebook and can run our plot and look at the same data set we were looking at before with the same colors. So this way you can actually interact in Python with the data in this kind of third-party tool. And there's some interesting stuff going on here. It's actually hard to get the two servers to connect. You have the same origin problem that JavaScript programmers might be familiar with. But we were able to get around this. So You know, there's still some work to do, but I'm hoping that this could be kind of a proof of concept for people who have these third-party services and would like to make them interact with Python. You can do a lot. All of this is happening at the client level. We have the embedded client that owns the data, which is sending it to the IPython client, and you can interact, and we have the framework in place to send that data back and forth. So that's what I have. Thanks.
Thank you, Jake. That's certainly a cluster of great software. So next we have Marcel up. Oh, sorry, Nick, you're always one away. So now you're still one away. So.
Always one away.
Okay. Hello, my name is Marcel. I'm from Brazil. By the way, I'm very glad to be here. It's an increase of 400% of people in Brazil here. My last time here was 1 people. Now we have 4. So yay. I work on a company in Brazil called Até Passar. It's a educational social network there. I'm the data scientist. And it has about 500,000 of users, students there in the social network. For there, if you want to get a public job in the government, you have to pass exam. So a lot of people studying to pass, and we have this social network to integrate all people. And they share content, and they also follow people as the Twitter, follow and have friends, etc. So my work there, I was requested to do a kind of a snapshot of the social network. So to know how there are the connections between the social network. So I developed this Python library using Python and PIL, Python image library. And it's open source. You can fork it and use it at my GitHub. And the idea is simple. It's a Python script that you can create visualizations using latitude and longitude from the social networks. It's very good for social analysis. So Facebook done this at his social network, and I imagine why can it do this in Python? So this is the plot I created using Python. Imagine this is the plot of Brazil, the 100. So there is a lot of connections in northeast. Southeast is the best places there. There are the good salaries. So a lot of people there in connections. And all it's done with Python and PIL. So you can use also this library for your own if you want. I put help. So it's a Python script. You can put input file. And you can define the output file, the color map, and define also the size of the image. So the input file is a pico file, yeah, and they have the tuples of latitude, longitude, and the quantity of connection between the latitude of source of destiny. So, for example, in this case, I call this Python script, passing the parameter the pico and the output image, and that's it. So other people start to use my library. This is Spain 20. Other guy, Andreas, use my library. So it's kind of libraries, kind of plots that you can use this library. Okay, it's open source. You can use it anywhere. Thank you very much.
Thank you very much, Marcel. All right, Nick, you're finally up. You're now 0 away. Travis Oliphant, if you are in the room, you are next up. He does not seem to be in the room. So it's Marianne after that. And I know she's in the room.
Okay, hi. My name is Nick Labello, and I work at the Research Computing Center at the University of Chicago. So I wanted to share with you today an application of all of the tools that I've been hearing about. I'm sure we've all been hearing about this week. This is for an image processing problem of the organism that you see on this, that I see on my screen. This little guy, just C. elegans. I work in a capacity which is something as a intermediary between high-performance computers and system admins, and then scientists, researchers, and graduate students at the University of Chicago. I have a background in chemistry, but now I have a position that is a research support position where I work with these guys to port their codes and get them running on a high-performance computer for the first time. So this particular application comes from the Byron Lab, where they do large-scale image processing of this organism. The goal of the application is to take and identify the worm, the organism, and identify certain properties of it, like the head and the tail. Okay, so by itself, probably not that difficult of a problem. It's been solved many times in many languages. What makes this kind of an interesting application of the scientific computing stack is that they're doing high throughput on the order of 10 to 30 hertz image capture, so up to 30 images per second. Their experiments are 6 orders of magnitude greater than the resolution that they're capturing at, so 12-hour experiments at 30 frames per second that they're writing to disk. And so you know, that brings you up to about 100,000 images that may need to be processed. They don't capture one organism at a time. They may do 5 or 6 under that microscope, which gets you very quickly to about 500,000 images in a 12-hour period. And then on top of that, there's about 10 or 12 microscopes in the lab. And so we very quickly arrive at the situation where they have more than 1 million images a day to process. So our solution here, when I began working with them, was to take this gigantic stack of scientific computing tools from Python and a big high-performance computer at the university's data center, and then mix them up to give them a little bit better throughput. So the situation that they were in was 1 day of imaging and then 5 or 6 or 7 days of waiting for that computer to crank. So the route that I took was to use a lot of NumPy and SciPy ND image. Kind of the very basics of it here is to take a few images and generate a composite background. NumPy lets me do this in about 1 line of code or so, to go from a bunch of worms to having an artificially generated background. I can take that background and again, in like 1 more line of code, subtract it from these images, and I'm left with a very clean picture of the organism itself. Without all that much extra work, thanks to scikit's image, and again, ND image and some other image processing libraries, I can identify the sides, the head, the tail, and then properties determined from that, like the midline of this guy. And just as an example of that, to get the border, so the red and green in this image, I just wanted to point out this is what the function looks like in my code. Get border has 12 lines of documentation and exactly 1 line that I wrote, which is buried in the return statement. So, thank you, SciPy developers. Okay, the result here is we took them from their serial code to something that is essentially trivially parallel. Their data sets are 100,000, 500,000 images per set on a problem that can parallelize out on as many processors as you have images. So this x-axis, I've tested it out to about 1,000 cores, and I'm quite certain that it could go out to 50,000 or 100,000 if I had that many processors to work with. So that's it. The actual biology has been accepted and will be published in the very near future. And the code will go on to Git when the paper is published. So thank you.
Worming our way into other fields, I see. Oh, sorry. I'm the MC. What are you going to do? So next up we have Marianne, and then after that, if Travis shows up. Oops, sorry. No, you need to use. Oh, yeah, it's just on this side. And then if Travis shows up, we'll do him. And then if not, it is Pedro is up with Gmode running. So, and then we'll do presentation mode. There you go.
It's not quite right, though. It's not the full screen. It's the, can we Can I zoom out? View. Command. Great, thank you. And yeah, okay. All right. Thank you. I want to talk about PyLadies because I think it's really great to have a worldwide organization that supports the participation of women in the Python open source community. But more specifically, I wanted to tell you how easy, straightforward, and fun it is to create your own local chapter for it, because you know, a worldwide group is great, but it's, you know, in everyday life you don't necessarily, you know, experience that support, even if it, you know, it's there all over the world. So with Julia Evans, who is a fellow Pythonista in Montreal, a data scientist and a great inspiration for all of us, at least for me. I launched recently PyLadies Montreal. I got a lot of support from the guys at Montreal Python, which I'm involved with in the first place. So PyLadies work a lot with meetup.com, so we decided to have our own page, and from then we could reach out very, very broadly to people you would not normally meet at tech events. And we recently had a real successful event. We used Wakari for it, and that was super convenient, so thumbs up to Continuum Analytics. We got amazing feedback. People loved it, and they want more. What else? Well, I'm looking forward to meeting the PyLadies Austin chapter, because we're here at Austin. But okay, hello, let's catch up. And I did meet some PyLadies Seattle people 2 weeks ago at AdaCamp San Francisco. And we're growing like every day. There are new people from all over the world: Austria, Tunisia, Taiwan, Canada, many places. So it's really quite informal. Your events can be more social, more technical, a mixture of both. It's just good to know that there's a strong demand and there's lots of fun to have. Thank you.
All right, so next up we have Travis Oliphant, who is here, and then after that we'll have Pedro. So.
All right, thanks, Anthony. I'm just here really just to give a status update and then kind of talk about some of the things that are happening. We're doing a lot of things actually that I think are pretty exciting, and I know we don't get the word out to everybody. Who's here? Who's heard of Numba here? Anybody used Numba? Anybody used it? Okay, so it's getting better. I mean, it's better and better. It still is a pre-1.0 product, but it's a lot better than last year when I came and demoed and it didn't work. So it's made some strides. In fact, the documentation has gotten a lot better. And if you look, 0.9 just came out. You can see all the different version 0.8 is not the docs aren't uploaded yet, but the dev documentation, it actually shows there's a lot of information there about we're adding annotation, so the ability to say annotate your JIT compiled code so that you can see the type inference that went on. I mean, typically what happens is if it's still slow, it's because the type inference is still using Python objects, and so you can see the result of the type inference and see the Python objects. You know, and then you can also build it like Python. You build an HTML page that'll show you the LLVM IR that actually outputs from the JITted code. So many of you who don't know what Numba is basically a translator from Python syntax to LLVM IR. And by doing that, you can actually write loops that deal with type containers, and by using the type information of a NumPy array, you can build code as fast as C or C++. It's sort of another way to write code, and you can do it very, very quickly. So it's made a lot of progress in the past year. It's got a no Python mode, which raises an error if it tries to go to the Python syntax. If it ever tries to use Python objects, it'll just raise an error. That's no Python mode. Definitely want to advertise that, because sometimes that's a way to tell, hey, I'm not making this fast because no Python mode is giving me an error. That means it couldn't figure out how to put the types, lower the types down to machine levels. Support structures. There's a vectorize function inside of Numba. So if you've ever wanted to build a ufunc in NumPy, and didn't want to write some C code, you can just put a decorator around your scalar function, and now it becomes a ufunc immediately. Very easy to use. So it's made a lot of progress, and you can write a lot of fast code. There's been some progress around it. I wanted to just briefly talk. There's some. I'll point you here, and you can play with it. Wakari.io's Travis. If you go there, you'll see my bundles that I've shared, and I've shared several IPython notebooks, including a J0 and Numba, which is one of the first things I did in SciPy was create the special library, all these special functions. And the Bessel function, if you look in there, it's a CFES code. It's just all C code. And here I've recreated that same C code, but now all in Python syntax. And you can see the polyeval, and I've jitted that down to tell it what types it takes and what type to return. And there's some arrays that define the polynomial. It's basically a Padé approximation. And you can see all that code. That's just basically a rip from the CFES C code. And you compile that down, use the vectorize to take this scalar function and create a numpy ufunc out of it with a simple vectorize. Numba.vectorize, you pass in that J0 Python function and get a vectorize function out. And now I can call that vectorize function on a linear space of data. And that code takes 80 microseconds to run, which is the same speed or faster than the SciPy special J0. So in Python, I've done exactly the same thing as you can do in C and C++, but it's faster. And I would argue that's a little easier to maintain if I have a bunch of Python code than a bunch of SciPy code. So it's definitely possible to essentially, you could rewrite all of SciPy using Numba at this point. I'm not saying we should do that. I'm just saying that's possible. And one of the reasons for working on this is to make code easier to maintain. So it's made a lot. It's still pre 1.0. 1.0 we're working towards more robustness, more capability. Not really more capability. It's more robustness and more people using it and reporting problems they're having. So make sure we're covering more and more of the language. At some point, we'll try to push it to the NumFocus Foundation. I wanted to advertise the NumFocus Foundation. It's getting a lot of support. We just sponsored the Python Women in Science and Technology event, and there is also money for a technical fellowship. So if somebody is interested in sponsoring some of their graduate work, working on any kind of, you suggest what your project you want to work with, anything in the stack, make a proposal to the NumFocus Foundation. Several of the board members are here, and there's money available to sponsor a student and a mentor. So that's it. Any questions? Great.
Well, thank you very much, Travis. Next up, we have Pedro. And after that, if we could get Thomas in staging with the SciPy Stack Talk.
Oh my God. Good evening. I'm Pedro. I'm from Brazil, Observatório Nacional. And I apologize for any spelling mistake because English is not my mother language. And I will show you all my work I did in my master's. I was obliged to implement and to use this clustering method. Oh, it's not. Oh, it's not showing. Okay, just a minute. Oh my God. Yeah. Okay, so I was obliged to use and implement the Gmode. That's a clustering method. So it's an old method. It's only my field, asteroids and lunar geochemical samples. So I was obliged to use it and implement it. I tried to make it better. Using, of course, Python. And, okay, the old Gmode was developed by Gavroschin and Corradini. It's a Russian and Italian guys in the 70s. He's only known in the lunar geochemical field and the planetary sciences. And originally was coded in Fortran 5. I don't know even it's possible to compile this code. Okay. So Gmode had a correction for covariance, so misaligned clusters was not well recognized by it. And I implemented the adapted Gmode clustering method using NumPy, SciPy, and Matplotlib. I tried to make more standalone as possible. I had to explain that I learned Python when I was implementing this method. So I started learning NumPy, I started learning SciPy and Matplotlib. So that's how we ended my coding. Yeah. Okay, so you can find me on GitHub. There's my version of Gmode there, and on the Facebook. Okay, so now I want to show you all how it works. You can import it. Okay, so you call it. Okay, imported. I recognize the developers, you know. Okay, I'm not the guy who wrote the method. You load your data, okay, and you run it. Okay, and then you wait a little because it's not opinionated yet. I'm thinking to go into. I use Cython to make it a little more faster. It's about 200. The sample is 200 points, bidimensional. I simulated three Gaussians in a space of two variables and some random points. I'm going to show you some pictures. So you can evaluate the variables if the variables are important. Are separating the clusters, and you can show all the matrix, the distance matrix, and you can see like the statistics of each cluster, and you can see the members. So the members. Okay, go, and you can also. Oops. I think the IPython guides told us about this stuff. Okay. You can run it in a single line if you want. If you don't want to load it in a IPython and a Python interpreter, and does the same thing. Okay, and you can see the results. Okay. Okay, Larry. Here he goes. Okay, he's going.
And thank you very much.
Sorry.
So close, so close. Thank you. All right. I've ran out of clustering puns, so you all are lucky. For our last talk, we have Thomas. Who'll be talking about the SciPy stack.
Right, so I just wanted to give a bit of background on this concept of the SciPy stack that some of us are pushing. It's a bit of a branding effort. I realise that branding can be a dirty word in tech circles. It's an idea that a lot of different people have had over the years in one form or another. The current incarnation got started after Euro SciPy last year. We realised that there's kind of an unofficial scientific Python standard library made up of these sorts of packages that, like, all the people in this room have probably got at least the top row of these packages all installed, and probably many of you have got the bottom row there as well. But there isn't any like obvious list of these or anything for new users, and all the community websites, scipy.org and whatever, were just listing how to install one package at a time onto a Python installation that you've already got. So in terms of competing with things like R or MATLAB, where you can just, you go to the website and click download and you get one unified thing, it wasn't, we weren't in a really good position. Obviously, there were things like EPD and Anaconda, where you do get one unified download, But from the from the community angle, from the SciPy angle, we weren't really displaying that. So we had a very long, heated discussion on the mailing list about what packages should be in some kind of a standard. And there were some people who felt that it should be a smaller set and some people who felt that it should be a rather larger set. But these six projects, plus obviously Python itself, plus Nose for testing, we decided are the standard components of the SciPy stack. And if distributions want to say that they're distributing the SciPy stack, then they have to include all of these things. And the new SciPy website, which we launched a couple of weeks ago, now has a list of these distributions. So when you go and click install, the first thing that new users see is Windows and Mac users, you probably want one of these. So we've got a bit more unity there, and we also hope that this can be a bit of a sort of kind of like a scientific Python standard library from a development point of view. So if you're developing a more specialized package, then we hope that increasingly as this idea takes off, you'll be able to rely on most users having this combination of packages, so you don't need to implement so many fallbacks for when, you know, SciPy isn't installed or whatever. Some other ideas that people on the mailing list came up with, that we said we're not going to do at the moment, but we want to, you know, we'd love to see some of these things done in the future, is to link up and unify the documentation for these different packages a bit more. So they're currently sort of spread out over all of our projects, different websites, all in sort of slightly different formats and color schemes, and that's not necessarily a bad thing. But we could probably do a better job of connecting them. More ambitiously, we could take on the Python packaging mess, as it's been called. So if you've used R, you'll know that when you install a package in R, it generally works quite reliably. It just goes and fetches it from cran. Admittedly, it's got a rather smaller set of packages than Python has to work with, but there's also things they do, like ensuring that every package has a Windows and a Mac binary build, so it's much more sort of reliable to install things, and potentially more interoperability between packages. So, for instance, like a few weeks ago, I built a SciPy equation to represent a model of something in my work, and then I wanted to fit the model to data using SciPy optimize. I had to go and completely sort of rewrite that equation as a Python function, and we can think of ways that sort of thing may already be ways that can be done. I'm out of time now, so thank you very much.
Thank you, Thomas. It is now time for the mini symposia and some BOF, so please go enjoy those events. And we'll see everyone back in here in the morning for the keynote and at the reception this evening, right over there in the Tejas room at 7 p.m.